Assalamualaikum and hi. Here I'm going to proceed with 7.2 Chemical Properties of Haloalkane. So learning outcomes end of the lesson, students should be able to explain nucleophilic substitution reactions of haloalkane, B. Explain SN1 and SN2 mechanisms, C. Explain elimination reactions of haloalkane, and then the last one, explain the use of haloalkanes in synthesis of Grignard reagent RMGX or ARMGX. For chemical properties of haloalkanes, we will discuss on types of organic reaction in haloalkane, which are nucleophilic substitution reaction and elimination reaction. Also, the synthesis of Grignard reagent. In nucleophilic substitution reaction, there are 7 reactions involve haloalkane. So, 2 types of mechanism, either SN1 or SN2. For synthesis of Grignard reagent, for preparations of alkane, primary alcohol, secondary alcohol, tertiary alcohol, and also carboxylic acid. Chemical properties of haloalkane. The carbon-halogen bond in haloalkane is a polar bond. It means it has difference in electronegativity. Halogen is more electronegative compared to carbon. Haloalkanes are reactive and undergo nucleophilic substitution and also elimination reaction. Carbon with partially positive charge is bonded to X with partially negative charge. So carbon has electrophilic site that make it easier for nucleophile to attack. In nucleophilic substitution reaction, electron-rich species that is nucleophile attacks the partially positive charge of carbon atom that is bonded to the halogen with partially negative charge. So here are the general reactions of nucleophilic substitution reaction. As a result from nucleophilic attack at electrophilic site, the CX bond, which is a polar bond, undergoes heterolytic cleavage because of difference in electronegativity. So, nucleophile replaces the halogen group while X- or halide ion becomes a leaving group. So this note is to simplify the reaction involved in haloalkane. So the first reaction involves aqueous solutions of sodium hydroxide where hydroxide ion as nucleophile. So product form alcohol. So this is the general equation for the first reaction. Second, we have water as compound, so nucleophile H2O. So product form alcohol, and then this is the general equation for the second reaction. Third reaction involve potassium cyanide. So nucleophile we have cyanide ion, product form nitrile compound, and this is the general equation. The fourth equation involve ammonia and NH2- as a nucleophile, and product form is a primary amine. So this is the general equation for reactions with ammonia. Next, compound alcohol, nucleophile alkoxide ion, product form ether. So this is the general equation. And sodium alkoxide, RONA, nucleophile alkoxide ion, product form is the same, ether, and also general equation. So sodium ethanoate, CH3COO-Na. So nucleophile is ethanoate ion, product form ester, RCOOR, and this is the general equation involving sodium ethanoate as the reactant. First, hydrolysis of haloalkane with aqueous solution of sodium hydroxide. Alkaline hydrolysis is carried out by boiling haloalkanes with sodium hydroxide aqueous to form alcohol. So haloalkane, sodium hydroxide aqueous, reflux to form alcohol and sodium halide. So for the first example, as we can see here, we replace bromine atom with OH. So OH comes from sodium hydroxide as a nucleophile. So this indicates that the reaction undergoes nucleophilic substitution reaction. Number 2, reaction of haloalkane with potassium cyanide. When haloalkanes is refluxed with KCN in alcohol, the halogen atom is substituted by the cyanide ion to produce a nitrile compound. So as we can see in example number 2, so bromine atom is being replaced with Cn. So Cn minus comes from KCN. So Cn minus in this case is a nucleophile. So this indicates that the reaction undergoes nucleophilic substitution reaction. Reaction number 3 is the reactions of haloalkane with ammonia, NH3. When haloalkanes is heated with excess concentrated ammonia, the halogen atom is replaced by amino group NH2 minus. So for example 3, as we can see, chlorine atom is being replaced with amino group NH2 minus. So note that using excess ammonia will produce only primary amine. The fourth reaction is reaction of haloalkane with sodium alkoxide. When haloalkanes is heated with sodium alkoxide, the halogen atom is replaced by the alkoxide group OR-. So it will form ether as the product. So for example 4, as we can see here, chlorine is being replaced by alkoxide group OCH3. Reaction number 5, reactions of haloalkane with water. When haloalkane is react with water, the halogen atom is replaced by the hydroxide group to form alcohol. So example 5, as we can see here, chlorine atom is being replaced with hydroxide ion to form alcohol. Reaction number 6 is the reaction of haloalkane with alcohol, ROH. When haloalkane is react with alcohol, the halogen atom is replaced by the alkoxide group OR-. So it will form ether as the product. In example 6, as we can see here, chlorine atom is being replaced with alkoxide group OCH3 and ether as the product. Next, reactions of haloalkane with sodium alkanoate. When haloalkanes is react with sodium alkanoate, the halogen atom is replaced by carboxylate group. So we will get ester as the product. So as we can see here, chlorine atom being replaced with carboxylate group. So we'll get ester as the product. Exercise 1. So first question is reaction of haloalkane with excess ammonia. So as we can see here, so chlorine atom will be replaced with amino group NH2- to get primary amine. So for second question, so this is the reactions of haloalkane with sodium alkanoate. So B should be a haloalkane. So in this case, X from haloalkane can be either chlorine or bromine, is replaced with carboxylate ion RCOO- to form an ester. For the third question, so this is the reactions of haloalkane with alcohol or sodium alkoxide. So meaning C can be either alcohol or sodium alkoxide. In this case, halogen or chlorine atom from haloalkane will be replaced with alkoxide ion to form an ether. The fourth reaction is haloalkane with cyanide compound. So in this case, we use sodium cyanide instead of potassium cyanide. So bromine atom from haloalkane will be replaced with cyanide ion to form a nitrile compound as a product. Okay, this is the answer for the question. So A is actually a primary amine. Okay, so how to determine a primary amine? So primary amine is actually when you have one carbon atom directly bonded to nitrogen atom. So this is a primary amine. So for B, okay, the X could be either bromine or chlorine, and C, okay, reactions with alcohol. Okay, so substitutions of chlorine with hydroxide ion to form an ether. And then D, okay, substitutions of cyanide ion, okay, from bromine to form nitrile compound. In nucleophilic substitution reaction, there are two types of mechanism depending on the structure of haloalkane, either primary, secondary, or tertiary. So SN1 stand for unimolecular nucleophilic substitution reaction, while SN2 stands for bimolecular nucleophilic substitution reaction. The SN1 and SN2 reactions follow first or second order reaction kinetic. So S stand for substitution, N subscript nucleophilic, 1 referring to rate determining step involve only one reactant, while 2 referring to rate determining step involve two reactants. Let's compare SN1 and SN2 reaction. So SN1 involve unimolecular nucleophilic substitution, while SN2 bimolecular nucleophilic substitution. So SN1 undergoes first order reaction with rate equals to K concentrations of only haloalkane. For second order reaction in SN2, rate equals to K concentrations of haloalkane and also nucleophile. SN1 involve weak nucleophile, while SN2 involve strong nucleophile. In SN1, intermediate involve carbocation, while its SN2 transition state as intermediate. SN1 involve two-step mechanism, while SN2 only one-step mechanism. In terms of order of reactivity, in SN1, methyl halide is less reactive compared to primary, compared to secondary, compared to tertiary, while in SN2 reaction, order of reactivity of haloalkane from tertiary to secondary to primary to methyl halide. So in SN1, steric factor is not that important, but as in SN2, steric factor is important. SN1 reaction is the first order reaction. It involves the formation of a carbocation. So rearrangement can occur to form a beta carbocation if possible. Recall that the first step in the SN1 is that the leaving group leave to give a carbocation. Therefore, a rearrangement can occur to give the more stable carbocation, which is then attacked by the nucleophile. The rate of reaction depends on concentrations of haloalkane only. So the strength of the nucleophile has no effect on the rate of reaction. SN1 reactions are governed or ruled mainly by the relative stabilities of carbocation. Tertiary alkyl halide or tertiary haloalkanes react rapidly by a mechanism that involves departure of the leaving group prior to substitutions of nucleophile. Relative reactivities of haloalkane in SN1 reaction. So methyl is the least reactive haloalkane compared to primary, compared to secondary haloalkane, compared to tertiary haloalkane, meaning that tertiary haloalkane is the most reactive haloalkane in SN1 reaction. Relative reactivities of SN1 reaction is based on more stable ion, requires less energy to form the product. So tertiary haloalkane is the most reactive haloalkane towards SN1 reaction hydrolysis compared to secondary, primary, and methyl halide. While for SN2 reaction, it is a second order reaction that the process of breaking and bond formation occurs simultaneously. Nucleophile attacks at the site opposite to the halogen minimize the repulsion, so the intermediate species form is called the transition state. The stronger the nucleophile, the higher the rate of reaction. The reactivity of SN2 reaction depends greatly on the size of the group attached to the CX atom that being attacked. The presence of bulky alkyl groups will prevent the nucleophilic attack. Relative reactivity of haloalkanes in SN2 reaction are as follows. So tertiary haloalkane is the least reactive compared to secondary, compared to primary, compared to methyl. SN2 reactions are governed or ruled mainly by steric factors or steric effect, meaning the more alkyl groups connected or bonded to the reacting carbon, the slower the reaction. So carbon must not be sterically hindered. Tertiary halide do not react via the SN2 mechanism due to steric hindrance. So now, let's see what is meant by steric hindrance and steric effect. Steric hindrance can be defined as the spatial arrangement of the groups near the reacting site hinders, retards a reaction. Large group can often hinder the formation. Steric effect is an effect on relative rates caused by the space filling properties of those parts of a molecule attached at or near to the reacting site. For primary haloalkanes with large alkyl groups, it will not undergo SN2 reaction due to steric hindrance. So this is the bulky alkyl group, okay, in this haloalkane. Instead of undergoes SN2 reaction, so it will undergo SN1 reaction by forming carbocation. In elimination reaction, dehydrohalogenations of haloalkane involve removal of halogen and also hydrogen from an adjacent carbon to form a carbon-carbon double bond, which is alkene, in the presence of strong base. Okay, for example 12, okay, we want to remove halogen and also hydrogen from adjacent carbon atom, either from the right side or the left side of the carbon that bear halogen. So if we remove hydrogen that on the left side and also halogen, so we'll get the major product. While if we remove bromine and the hydrogen from the right side of the carbon that bear halogen atom, so we'll get minor product. So to determine major and minor, so we have to apply Sitzeff rule. According to Sitzeff rule, most highly substituted alkene is the most stable alkene. So the most stable alkene will produce a major product. So in this case, so compound A has 1, 2, and 3 alkyl group. While for compound B, it has only 1 alkyl group. So for second example, we want to remove bromine from the carbon and also hydrogen from the adjacent carbon atom. If you remove hydrogen from this carbon, so you will get the minor product. If you remove bromine and also hydrogen from this carbon, so you will get the major product. So how to determine the major and minor is based on Sitzeff rule. There are two different types of organic reaction. So if you are using strong base in ethanol, it will lead to elimination. While if you are using strong base in aqueous, it will lead to nucleophilic substitution reaction. So the examples are as follows. Synthesis of Grignard reagent. Grignard reagents are called organomagnesium halides. It has empirical formula of RMGX. Grignard reagent is prepared by the reactions of haloalkanes with magnesium metal in anhydrous ether, also known as dry ether, as the solvent. The Grignard reagents undergo many reactions that makes them useful as a starting materials in the synthesis of other organic compounds. These are the uses of Grignard reagent. When Grignard reagent is reacted with H3O+ in dry ether, it will form an alkane. When it reacts with methanol in dry ether followed by hydrolysis, so it will form primary alcohol. If Grignard reagent is reacted with aldehyde in dry ether followed by hydrolysis, it will form secondary alcohol. And when it reacts with ketone in dry ether followed by hydrolysis, it will form tertiary alcohol. And the last uses, when it reacts with carbon dioxide in dry ether followed by hydrolysis, it will form carboxylic acid.